Now here comes a important question. Let me write it down because give you some time. What would happen if I replaced the IDFT with the DFT? Go back, look at the figure. What would it would be? The delay chain would remain as is. You would have replaced this instead of the W dagger, it would be the W matrix. Okay. So, let us see if we can, of course, by now you can easily tell that the outputs will be the same except they are shifted, basically shifted around. Let us just confirm that that is the case. So, if I write down xk prime of n, the primes denote that now I am working with the DFT matrix sitting there. This is equal to summation I equal to 0 to m minus 1 Si of n. Notice that now it is the DFT matrix, it is W subscript m superscript ki. Okay. If I now take the Z transform, it will be xk prime of Z, that will be equal to summation I equal to 0 to m minus 1 Si of Z Wm ki. Please go ahead and substitute. You can show that this is equal to x of Z summation I equal to 0 to m minus 1 Z Wm minus k raised to the power minus I. Okay. And you can verify. So, this tells me that this is the following observations that we get. H naught prime of Z, that is the filter transfer function between xk prime x0 prime of Z and x of Z. This comes out to be 1 plus Z inverse plus Z minus 2 dot 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 plus Z power minus m minus 1. Oh, this is nothing but H naught of Z. So, the basic filter did not change, of course, that we knew already. Okay. Now, H1 prime of Z, this will come out to be 1 plus ZW inverse power minus 1, basically I am substituting from the expression above, ZW inverse the last term raised to the power minus m minus 1. Okay. And if you simplify, you can show that this is nothing but H naught of Z W minus 1, which is in our terminology, this would actually be H of m minus 1 of Z, because this itself is as if you are writing H of minus 1 of Z, and these two are the ones that are linked. Basically, whatever you call as minus 1 already has a name, H, that is H of m minus 1. Okay. So, H prime of Z, and of course, you can go through and verify that the final filter H m minus 1 prime of Z is nothing but H1 of Z. Okay. So, again exactly the result as before, maybe the figure to look at is this expression. H naught of Z is from input to the topmost branch, H m minus 1 to the next branch, and all the way to the bottom is the next branch. Okay. So, here is a pictorial representation. If this was what you obtained with the transpose conjugate matrix, now with the analysis that we have done with the DFT matrix, the figure is as follows. Okay. Let us quickly draw it. What did we do? We said that we will have a vector which is S naught of n, S1 of n all the way to Sm minus 1 of n, and we are going to pass it through the DFT matrix. I am not calling it time or frequency, I am looking at it as a transfer function, and this produces for us x naught prime of n, x1 prime of n, and all the way to xm minus 1 prime of n. This is what is the, think of it just strictly as a transform, and what this transfer functions between these corresponding filters is as follows. Okay, again let us draw it very quickly, it may not look very pretty, but this is, so this is H naught, this is H naught prime, okay, and the next filter that we have, this is H1 prime. No, this is H1 prime is not this one. This is actually Hm minus 1 prime. H1 prime actually will be all the way to 2 pi. Okay. This is H1 prime. H2 prime, this is H2 prime, H2 prime, and this, the last one is Hm minus 1 prime. Okay. Now, can you give me a interpretation of what happens when you take DFT of a vector? So, how did you get x naught of x naught prime of n? You took the input, passed it through a filter which was basically a comb filter, and then you observed the output, right, and this S naught, S1, Sm minus 1 are all delayed versions. It is basically like the input signal, that is what you have taken. Now, can you give me an so when you take the DFT of n variables, what exactly are you doing? You are passing that signal through a bank of filters, and the bank of filters go all the way from 0 to 2 pi. Of course, you can do not worry too much about the notation. Basically, it has m filters and you get the output from those. Last step, very, very important step, but this is not what we do in DFT, right? What is this? If this is x of n, this is x of n minus 1, correct, all the way to x of n minus m minus 1, okay. But that is not what we do in DFT. Actually, what happens in DFT is the following structure: Z, it is not a delay chain, but it is an advance operator, and each of these branches comes in, and then we take the DFT of this vector, DFT of this vector. Am I correct? Because what is usually fed into is x of n plus 1, x of n plus 2. Basically, if your input sequence is let us say is x of n plus 1 dot dot dot, you say that okay, I am going to take the DFT of this vector. So, you take a block of length m, and you take the DFT of it. So, this is more likely what we will encounter. Okay. So, these produces the m outputs. Now, like before, let us quickly label them. If this is x of n on the upper branch, you have x of n, this will be x of n plus 1, this is x of n plus 2 dot dot dot, this is x of n plus m minus 1, that is the last branch that is feeding in. Now, like before, for systematic approach, label this as S naught of n, this as S1 of n, and this as Sm minus 1 of n. Okay. Outputs, let me call this as x0 of n, x0, x1 of n, x1 of n, xm minus 1 of n. Again, I am treating it strictly as a transform. This n is actually showing you the time index. So, there is a vector at the input, there is a vector at the output, input output relationship is through the DFT matrix. So, please write down that expression. Again, it is a repetitive one, but it actually gives us a important insight. Xk of n is I equal to 0 to m minus 1, Si of n Wm minus Ki. No, there is no minus, this is the DFT matrix. So, it is power ki, you can show that this is equal to just one step and we are there with the answer, x of z summation I equal to 0 to m minus 1 z w m k raised to the power I. Okay. Very, very important. So, what is h naught of z? Set k equal to 0, it will be equal to 1 plus z plus z squared plus last term z power m minus 1. This is a comb filter, but going in the backward direction, non causal. But this is the same as again easy manipulation. If you take z power m minus 1 as a common factor, what you will get is 1 plus z inverse plus z power m minus 1. So, on the unit circle h naught E of j omega, this is nothing but a phase term. If you take the magnitude response, it goes away. So, what is the magnitude response of your h naught? Same as what you did for when you had the transpose conjugate of the DFT matrix. So, if you go ahead and now work out hk of z, it will come out to be very, very interestingly h naught of z w k. What happens when you have a delay chain and the transpose conjugate matrix? You get the filters in the correct sequence. You replace the transpose conjugate of the DFT matrix with the DFT matrix. You get the same outputs, but the output sequence is scrambled. Now, if you change the delay, keep the DFT matrix as the same, instead of the delay chain, make it into the advanced chain, then what you get? The sequence comes out again in the correct form. So, when I do the DFT, what is x1 of the x1 or the second DFT coefficient? It is nothing but the output of the filter that is just adjacent to the low pass filter. The first DFT coefficient is effectively the DC term, because this is the filter that filters out the DC. The second DFT coefficient is the one that is slightly shifted, basically low frequencies and so on and so forth, and the last of the filters basically is the one that goes very close to 2 pi. Okay. So, what is DFT? It is actually taking the input signal, passing it through a bank of filters and then giving you the outputs and saying, oh, by the way, x naught, you think of it as the frequency component. Usually if somebody gives you the DFT coefficient x naught, what is your interpretation? That is the DC term. It is actually not the DC term, it is actually all the energy that lies, that will pass through this filter in your input signal, that will pass through this filter is what comes out as x naught. And what is x1? Our usually expectation is that what is the signal component at e power minus j 2 pi over n, right, or omega equal to 2 pi over n. It is not omega equal to 2 pi 1 over n alone, it is actually so this corresponds to omega equal to 0. Okay. Now, x of 1, we say that this corresponds to the energy component at omega equal to 2 pi over m. Okay, it is not just 2 pi over m, it is all those components that will pass through this filter. The center is at 2 pi over m, yes, that is given the maximum weightage, but there are other components that are coming through as well. So, one of the key things to recognize is that until now what our impression of DFT was, okay, there is some magical means by which I do a transform and I get the frequency response at omega equal to 0, omega equal to 2 pi over m, 4 pi over m, 6 pi over m, and that is our impression, but that is not true. It is actually as if you took the information and passed it through a filter with a finite bandwidth. It is not infinitely narrow bandwidth, it has got a finite bandwidth, and any signal that passes through this filter will show up as a contribution to x naught. So, the question is in the context of the DFT, are we making a periodicity assumption? The first step that we do in the computation of a DFT. Let me just highlight that. So, if I have a long sequence x naught x1 dot dot dot, it is a very long sequence, okay, x of n prime dot dot dot, and I decide to take the DFT of one portion of it, let us say some let us say 128 points. This is a much longer sequence. So, if my input spectrum, the true spectrum, if my input spectrum let us say had this shape, the minute I multiply it with a rectangular window, I have modified my sequence. It is no longer this spectrum. So, actually what is the spectrum? It is this convolved with a rectangular window. Spectrum of a rectangular window is a sinc function. Okay. So, already I have modified. So, you have to go back and revisit saying, okay, what am I calling as the delta function, because the it is actually how we interpret the process. So, the minute I like to look at it, if I look at it from a filtering point of view, the minute you have multiplied the rectangular window, I have modified my input sequence. And then I take this sequence and I try to I compute the DFT. But the interpretation that we are giving is, okay, ultimately what are we trying to do? I am trying to get the spectral components of the input signal. That is the ultimate gain. So, the way I want to look at it is from a filtering point of view, instead of doing a rectangular window followed by a DFT, then sliding my data, doing another DFT, and doing through the process obtaining what is my spectral estimation. What we are saying is, hey, by the way, this is the same as passing it through a filter bank. So, you can take your data, do not need to window it, just pass it through a rectangular window based filter bank. So, this type of filter bank, this is exactly what your DFT is also effectively doing. Okay. So, again how the effect of the window affects the final spectrum, you may view it a little bit differently, but the ultimate the overall effect is that you can take the impact through the multiplication with the rectangular window, in which means that the original spectrum now has got modified. Or I can think of the signal, original signal, not windowed signal, original signal passing through a bank of filters, and then I am observing the output and I am getting, and the mathematical framework is the same, because if you look at what we are doing is exactly the same thing. You get a vector, you process it. Now the I have not yet finished the interpretation. So, if you just wait for the next set. Okay, the time is over. Let me just leave you with a few questions. Okay, I will definitely pick it up. We will clarify all these doubts because it is very important. I am glad you have asked those questions. Now, what would be the DFT interpretation in the following setup? So, my DFT center or the frequency points are 2 pi over m, 4 pi over m, 6 pi. Okay, let me just take the case where it's a 16 point, it's an 8 point DFT. So, I basically have 8 points between 0. The last one is 14 pi over 8. Okay. Now, supposing I had the signal represented a tone in between 2 pi over m and 6 pi over m, in between 2 pi over m and 6 pi over m. Take its DFT and see what you will get. And let me just sort of give you a feel for it. We'll discuss it in detail. You will find that the DFT coefficients will be strong, quite strong here, some component here, strong, it will never go to 0. Okay? You actually try it out. You can actually do a simple test and do it. Now, you know what the explanation for this is? Because if I took this why this last filter, why is it still having non-zero output? the last filter that if I were the filter bank interpretation says the last filter is centered around this frequency, it has got a response like this. So, when it comes here, this is the tone that is present. So, this is what shows up as the output. It shows as a non-zero output. So, one of the problems with the DFT is that if I have a tone in between two DFT frequencies, I will have non-zero components on across all the terms, not just the ones nearby, all the terms will have non-zero. And your supposing somebody gave you this blue lines and told you to interpret this spectrum, then you will say that there is strong components, you say there are two strong components at 4 pi over m and 6 pi over m. That is how you can interpret it. You cannot say that I suspect there is a so your interpret, and they will say that there are weak components at all others, which is a very erroneous interpretation of the spectrum analysis that you will get, but that is all you can do. However, if you now have interpreted, basically it is the same interpretation you will get whether you think of it as a filter bank or as a DFT operation. However, if you are willing to accept it as a filter bank operation, there is a way by which I can get you almost close to the answer that there are only there's most likely the best case is there are two tones, one at 4 pi over m and one at 6 pi over m. That's, and you can say that okay, if both of them are equally strong, it also could be that there is a single tone which is somewhere in between the two those two DFT frequencies. But it is possible to get to that point only with the filter bank interpretation. With the DFT interpretation, there is nothing we can do. This is, if you have a tone at in between two DFT frequencies, the spectrum that you will see will be something that could mislead in terms of its interpretation, and it is the inherent in the structure of the DFT, and this is well known. This is one of the artifacts of the DFT, and that is why interpreting the DFT as a filter bank actually gives us some interesting insights. And what are those insights? How do I make it very accurate or better than a simple DFT? We will look at it in the next class. Thank you.